works. Yeah, so welcome to the workshop. So you may submit your questions here at tinyurl.com, intro to deep learning dash Q&A. So this will lead you to a Slido website where you can submit questions that you have about the content or even questions about our CCA. So yeah, intro to DL dash Q&A. So what is NUS Statistics and Data Science Society about? We are a society that is committed to foster a community of students interested in data science. So we have hosted a lot of workshops that would serve to help data science students to, or even you don't even have to be part of data science. Basically, we have a lot of workshops to teach students more about deep learning, machine learning, statistics, etc. So we want to ignite interest in the field of statistics and to engage you with real-life applications. So occasionally we will have some hands-on exercises for you, but for this workshop today, we will be showing a demonstration of our code at the end. So we would like to bring the student body together and cultivate teamwork, and we want to support you in your academic and career planning endeavors. So just last week, we had a talk with Grab Singtel Digibank where we learned more about ML Ops, and through that, we also learned a bit about their career. And a few weeks back, we also had a career session that was also held by our events team. And yeah, so do check out our links that is sent in the chat here. So do follow us to keep yourself updated with our latest workshops and events. So today we will be having 4 presenters, and yes. So firstly, we have Javier Tam. Say hi.
Hi. Hello.
Yeah. Okay. And then we have Bhairav Shankar.
Hello.
And Vinod.
Hi.
Lin Weiliang.
Hi.
So they will be teaching you more about deep learning. So we will first start off with Javier.
Okay. Okay. So hi everyone, I am Javier and I am year 2 data science and analytics student. So well, first of all, I'd just like to say thank you for joining us here today. I know it's like week 10 and then it's getting super busy for everyone, but yeah, thanks for joining us and I hope you guys learn a lot from today. Okay, so here is the rough timeline. So I'll start off with an introduction. I'll tell you about some applications of deep learning, and then we move on to components and then after that, we'll go a little deeper into the math of how a neural network works. So once we know how it works, right, we need to know how to evaluate whether it's good or bad. So we'll move on to the analysis part. And then finally, we'll go head on over to Collab, where we'll show you how to create your own deep learning model using TensorFlow. Okay, before we get started, right, I just want to ask you, you guys a question. Like, do any of you have any examples of applications of deep learning? Do you know of any applications of deep learning that we might have come across? Oh yeah, I see one. Yeah, Siri, yeah, you're right. I mean, if you don't know anything, could you put like a cross or something? I just want to have a gauge. So yeah. Okay, I see a few crosses. Okay, yeah, that's fine. So yeah, so Siri is one application, I guess. Okay, now let's just get started with the different applications that you would have or you very possibly have come across in your daily lives. Okay, the first one is what we call recommendation system, or some people call it recommender systems. So stuff like if you notice, like your YouTube or your Netflix, you always have some videos there that they show to you, and they say stuff like things you might like. Or for Netflix, they have this because you watch something, and then they recommend you something. So yeah, this is basically recommender systems. where they try to predict what kind of stuff you like to watch based on your activity and like for YouTube, who you subscribe to and all this stuff. So in the past, they used machine learning, but more and more of them are using deep learning now. Okay, and next one we have autonomous vehicles, or you might know it as self-driving cars. So let's just watch this video from Veritasium.
This video is sponsored by Waymo. Start ride.
Make sure your seatbelt is fastened. For any questions, press the help button to speak with a rider support agent.
Okay. Now let's see where we go. It's looking at this car coming here. What's it gonna do? And it pulls in very smoothly behind it. No problems. Did not turn into traffic.
Okay, so that's a short snippet, right? But yeah, this is super cool. If you can see these kind of cars, they have a lot of sensors around, and then where they take in information and input. And then they use deep learning to figure out like when they should go or what to do during different scenarios. Okay, next we have, yes, Siri. Like one of you said, Siri, or you might know it, if you use Samsung, it'll be Bixby or like Alexa or Google Assistant. These are called virtual assistants. So they also use deep learning where they will try to, they can understand what you say, and then after understanding, they have to carry out some task. So all this is deep learning actually, if you did not know. Okay, yes, how can I not mention deepfake, right? So let's watch this video also.
Jordan Peele created this fake video of President Obama to demonstrate how easy it is to put words in someone else's mouth.
Moving forward, we need to be more vigilant with what we trust from the internet.
Not everyone bought it, but the technology behind such frauds is rapidly improving, even as worries increase about their potential for harm. This is your Bloom.
Yeah, okay, so very quick video. Yeah, so I'm sure some of you would have already come across deepfake before. And as his name suggests, deepfake uses deep learning also. So a more current example would be many companies using deep learning for such computer vision tasks. And yeah, there's no video, there's no audio for this, so we just watch it. Yeah, it's okay. So that's okay. What I'm trying to tell you guys is that, so deep learning, right? I mean, some of us, if we don't know about it, we might think that this is something that only professionals or like data scientists get to use. But actually, deep learning has such a wide range of applications, and it's used in so many things in our daily lives now, like our YouTube, Netflix, Siri, all those. So yes. Okay, now I'm sure some of you might have this question, right? Like you might be confused with these terms, AI, ML, and DL. They have been thrown around a lot recently in the recent years. And so you might be asking, so do they actually mean the same thing? Or are they interchangeable? What do they really mean? Well, if you do a quick search on the web, right, you usually come across something like a graph like that. So in the outermost, the biggest graph, you have artificial intelligence, AI. So, and then inside AI, a subset, you have machine learning. And then even deeper inside, you have deep learning. So from here, you can sort of tell, right, that these three are actually linked, but they are not exactly the same thing. So what is AI? So you can see AI, artificial intelligence, as the broad term or the umbrella term. So whenever you're referring to something or like a machine or a computer that mimics humans or try to imitate us in terms of learning and problem solving. So you can say that that's AI and you won't be wrong. And next we have ML, which is a subset of AI. So when we talk about ML, right, we are referring to algorithms that learn from data. So what are algorithms? They are basically steps and instructions to tell the computer what to do to solve a problem. So if some of you might know, is you have your regression and classifiers like linear regression, logistic regression, and life-based. But if you don't really know what this means, I think that's fine because it's not the main topic of today. So when we talk about machine learning, right, machine learning works well with what we call structured tabular data. So tabular data means data that can be put into tables, which means rows and columns. So you can see it of it as stuff that can be put in Excel. Okay, and lastly, we have deep learning. which is the smallest box inside. So it's a subset of ML. So deep learning mainly uses what we call neural networks, which is the main star for today's workshop. So remember, ML works with structured data. So actually deep learning also can work with structured data. However, it shines when it's used for unstructured data. So stuff like your text, image, video, and audio stuff. As you can see, this can't really be put into Excel, right? So this is what we call unstructured data. Okay, so far so good, right? Okay, let's move on to the components of a neural network. So why do we call it neural network in the first place? Well, it's because it's actually inspired by neurons, the stuff in our body, in our brain. So what are neurons? I guess, okay, if you don't take bio, right, it's fine, because I also didn't take, but I'll try to explain it to you in a simple way. So you can see neurons as information carriers or messengers. So this is one neuron. So in our body, every neuron is connected to a lot more other neurons. And then this is the structure. You have this tail-like thingy called dendrites. This is the cell body. This is the brain, which is called the nucleus. So what happens at these dendrites? So other neurons are connected to this neuron through the dendrites. And then they will send signals into these dendrites. And every time a signal is sent into this neuron, it's added up. So it keeps on adding and adding and adding until a certain threshold. When the signal is added up and it exceeds this certain threshold, it will trigger the neuron. And then this neuron will send an impulse through the axon, and it will send a signal out through the axon terminal to the other neurons. Yeah, I hope that is clear enough, right? So now let's try to keep this in our minds. And let's see what a neural network in deep learning looks like. So usually a neural network is depicted as such. So you have all these circles. You can see this as the neurons, or sometimes we call it nodes. So you can see each neuron is connected to a lot of other neurons. And we describe neural networks by layers. So the very first layer is called the input layer. This is where we pass in our information. So each feature will go into each node. And then the middle layers are called hidden layers, because we don't really know what happens in them. Okay, and then the output layer, the last layer is called the output layer. So this is where we get our prediction or output from. Now let's zoom in into these three neurons or nodes. And bam, you have what is called a perceptron. So a perceptron is actually a binary classifier. So what that means is that its output can only have two distinct values. So usually for simplicity, it's always 1 or 0. Okay. And then don't look down on the perceptron, okay, because even though it looks so simple, because it's actually, a perceptron is actually a neural network. It is the smallest neural network. And sometimes people call it one layer neural network because it only has one input layer and then you have an output. Okay, so for our example, right, the input layer actually can have as many nodes as you want. But to make it simple, I'm just going to have two input nodes for this example. So each feature will be passed into each node, and we denote them by x1 and x2. So each feature will have their corresponding weights. So what are weights? Weights are basically how important a feature is. So for example, if x1 is very important, you expect that the weight 1, w1, is very high. And x2 is not so important, so w2 will be not so high. So why do we need this? Is to calculate what is called the weighted sum. So basically, you just take each feature, multiply by its weight, and then you add everything together. That is the weighted sum. Why do we need that? We'll go into that shortly. Okay, so every layer in a neural network also needs something called a bias. This bias is always equals to 1, and it has its own weight. So if you look below here, right, you see I excluded the x1 because the x0, because x0 is equals to 1. So there's no need to write it. Now, why do we need a bias in a neural network? So actually the bias is quite a complicated and advanced topic, but I'll try to give you an intuition for now. So let's just, okay, we disregard this feature for now, right? So our perceptron now only has one input feature. And then we'll see our weighted sum looks like that now. So does this look familiar to you? right? It has this form y equals to mx plus c, where c is the y-intercept. So your w naught, you can treat it as a y-intercept. So if you look here, you know, okay, so no, our neural network now, we treat it, this is a model. And notice that if you don't have a bias, no matter how much you change the gradient, it's only going to be able to rotate about the origin. However, if we add in a gradient, if we add in a y-intercept or the bias, we can shift the model. So you can see that if we combine this shifting with the change in gradient, we can make a lot of other kinds of models. So a bias is there to increase the complexity of your model, so it can do more things. That's just the equation, okay? Now let's get back to here. So how do we calculate the output? How do we determine whether it's 1 or 0? So we take the weighted sum and we do some non-linear computation. So there's 3 very simple steps. First step, get the weighted sum. Second step, we apply to something called the activation function. In this case, we call it G. And the third step, we get the prediction y hat. Okay, so very simple. So what is an activation function? So you can see activation functions as functions that take in weighted sum, and then they decide if the neuron should fire. So in the case of perceptron, decide if the output should be 1 or 0. Okay, and this is the most basic step activation function. It's called a step function because it looks like a step, right? So you notice, right, if your weighted sum is more than 0, it's going to output a 1. If it's less than 0, it's going to output 0. Okay, very simple. So actually, there are a lot of other activation functions, but these here are 2 more really commonly used ones, called the sigmoid and logistic function, and what they call ReLU, which is rectified linear unit. So by now, some of you might have realized that all these activation functions are non-linear. So if you don't understand what non-linear means, actually it's okay also. You just have to know that we need this non-linearity, right? Because we want, like the bias, we want to make our model more complex, so we can fit our data better and it can do more complex stuff. So another intuition, okay, for example, I give you these few data points, right? Now I ask you, give me a model that can separate these data points. So what will you do? Very simple, right? You just probably give me a line. This is a linear model. So if you can, so anything that lies on the left side of this line belongs to this group. Anything that lies on the right side belongs to the other group. So if you can always draw a line to separate the distinct groups in your data, this is called linearly separable. Okay, but what if I give you something like that? It's quite obvious there are 2 distinct groups, right? But can you draw a line? You can't even draw any line to separate it. Okay. Now, but you can draw something like that, some kind of circle. So you can do this, but it's not a line. It is still separable, but it is not linearly separable. So this is why we need non-linear activation functions. If we always use linear activation functions, we're only going to be able to draw lines and we cannot fit our data or do complex stuff. Okay, I hope that's clear enough. Okay, now, yes, it's quite a lot to take in, right? Now, hopefully through this example, you see that solidifies what we've learned. Okay, let me put in some context with you. Suppose our neural network is a classifier that classifies a fruit into a banana or a grape. And it takes in 2 features, the roundness and the size. Okay, so now these are points that are already labeled and plotted on the graph. Now, let's say I give you 2 new fruits and now you plot them on the graph. So for us, it's quite obvious, right, that this is probably a grape, this is probably a banana. But how does a neural network figure this out? Okay, so let's say we have trained our model already, and this is what we got. So x1 is the size, x2 will be roundness. So after training the model, right, we realized that the best weight for the bias will be -5, and the weight 1 will be 1, and weight 2 will be 2. So remember the 3-step process. First step, get a weighted sum. Second step, we plug it through an activation function, and the third step, we get a prediction. So if our prediction gives a 1, we're going to say it's a grape. If it gives a 0, we're going to say it's a banana. So let's just plug in the values and see how it does. Okay, for the first fruit, we have a size of 1 and a roundness of 3. So we do the first step, we get a weighted sum, is 2. And second step, plug it through the activation function, which is the step function in this case. And since 2 is more than 0, the step function returns a 1. So 1 is grapes. Okay, so fruit 2, we have a size of 1 and a roundness of 1. Plug it, get a weighted sum, is -2. We plug it through the activation function. Since it's negative, it returns a 0, and that's a banana. So as we can see, yeah, our classifier did quite well, right? But yes, of course, this is a contrived example, but I just hope that through this example, you can see, you can get an intuition of how the neural network actually works. Okay, remember before when I said a perceptron is actually the smallest neural network you can have. So you can actually add more layers, you can stack them on top of one another, you can add more neurons per layer, and you can do a lot of other stuff. So here's a graph of a few other examples that you can do. So yes, deep learning has such a wide variety of applications, right? The limit is just your imagination. Yeah, I guess this concludes my portion. And now I'll pass my time on to Bharath, who will go through and who will go deeper into the math of how a neural network actually works behind the scenes. Thank you.
All right. Thank you, Javier. All right. So everyone. Okay, so this bit is going to be very, very heavy on the math. So strap in and let's do this. All right. So let's just first get a grounding on our artificial neuron, our perceptron. All right. So you basically have the following in your artificial neuron. You have a bias term, which is always set to 1. Then you have the weights. So the weights basically determine how much say the input neuron has in the output, has in deciding the output. All right. Then you basically have your neuron over here with an activation function that we call G, right? Now, basically what comes into G is this weighted sum that we call Z, right? And then we apply this activation function on it that becomes G of Z. And that G of Z is our activation A, all right? Now, we basically have these input values. So input values can actually be the features in themselves or the activations of other neurons, all right? Now, as Javier mentioned, we really only start getting into the really interesting stuff because the perceptron's fine, but then it's boring. So what we need to do is that we need to start stacking neurons into layers, all right? So here we have a pretty simple neural network, right? So you have these 3 input nodes, technically 2 inputs and 1 bias. Then you have 1 hidden layer, then you have 2 hidden layers and you have an output. So what happens, so what's going on over here is that these inputs are feeding into this neuron over here. This neuron computes an output. This output then gets fed into this neuron, and you also have the bias coming in over here, right? Then you basically have this neuron computing its output, sending it over to this guy. This guy takes in this guy and the input as well as the bias, and it spits out your final output. So what ends up happening is that information from the previous layers feeds forward into the next, right? So that was simple, right? So we should see how our performance was. And yeah, we forgot one thing. We forgot to train our model. At first, we initially randomize all of our weights and biases. So the outputs are basically at random. So our problem is to basically try and figure out what weights and biases we actually need in order to get our neural network to function properly. Now, before we get into that, we need to clear up some notational hiccups, because one thing that really plagues a lot of people when they're studying deep learning for the first time, especially the theory, is all the notation that you have to keep in your head. All right. So here is a neural network with everything labeled, right? So you basically have these you have these layers over here, layer 0, layer 1, layer 2, layer 3. Layer 0 is your input layer and layer 3 is your output layer in this case, all right? Now, you basically note down the activation of a neuron by talking about its layer number in the superscript in brackets. This is not exponentiation. This is the number of the layer. And then this is the neuron's number in that layer. So for example, this guy over here would basically have his activation being A10. And this guy over here, right? This guy would have his activation being A11, all right? So quick question in the chat. Just answer in the chat or something. What would be the number given to this neuron? What is the activation of this neuron by that same logic? Feel free to just enter it into the chat or just unmute yourselves and speak out. All right. Yep, that's correct. Wait, no. We start from 0. Yep.
A20.
Yep. A20. Yep, that's correct. Yep. So this guy is A20 and this guy over here is A21. Yep. All right. So now that we have our activations down, let's move on to the weights. Now you basically have weight W, L, J, K. All right. Don't be too scared. Now W just means that it's a weight. L again talks about the layer number, but what do we assign as a layer number? We basically talk about the layer number that it leads to. For example, if you go from 0 to 1, the weights over here would have the superscript 1. All right. Go from 1 to 2, superscript 2, 2 to 3, superscript 3. Simple. Now you have these J and K, and this is where a lot of people get messed up. The first index is the output neuron. It's a neuron to which the weight actually leads to. So it's a neuron number in layer L, and K is a neuron number in layer L minus 1. All right. So as given over here, this goes from neuron 0 in layer 1 to neuron 1 in layer 2, right? So therefore its weight is the weight of this connection over here is denoted as W210, right? Now can anyone tell me what would this weight be over here? This weight going from A21 to the output layer. Feel free to use the chat again.
W332. The W301.
Yep. I think it would be 1 in this case because 0 is usually reserved for biasum, but yeah, that is correct. All right. Yep. So everyone's got that. So now what? We need to fix we have 4 steps in order to fix as in train our neural network. We basically have the feed forward, then we need to implement a cost function. Then we need to talk about gradient descent and finally back propagation. Now, these terms might seem a bit unfamiliar right now, but we'll delve into what each of those actually means, right? So feed forward is basically just running the neural network as it is. It's called feed forward because, again, information from previous layers flows into the next and to the next and to the next until we get our output, correct? Right. So now the activations of neurons are determined by those of the previous layer. So the final answer for a particular set of inputs is some function of those inputs and the layers W, all right? So y hat is basically our output over here. Then we have the weights of our layer L, and then it's some function of the weights of layer L and the activations of layer L minus 1. The activations of L minus 1 are again some function of the weights of layer L minus 1 and the activations of L minus 2, all the way until we get to the weights connecting from layer 0 to layer 1 and to the inputs, all right? And just a note, f of W A L1 is just G of W L dotted into A times L minus 1. That's just G of Z, all right? This is just another way of representing G of Z. Why we do this, we'll mention later. All right. So now that we have our outputs, we need to talk about how we can improve, right? Because if you do badly in an exam, you want to know just how badly you've done so that you can improve, right? So we need to quantify how different our output y hat is from our actual labels y. So we do this differently depending on the task that we're trying to do. Regression is where we're trying to predict some continuous values. So we tend to use mean squared error, mean absolute error, root mean squared error, and so on. As for classification, we tend to use cross entropy and hinge loss. For the rest of this demonstration, we'll be assuming a regression task with the mean squared error as our cost function, all right? So this is basically C of all of these is going to be y hat minus y whole squared divided by 2. Now, let's think about the cost function. The cost function measures how badly a network does, right? So it's a function of all of the weights W and inputs X, and it returns a single real value. So this is like an easy thing that we can just reference, and then that basically lets us see how badly a network is doing. So what we want to do is that we want to minimize how badly we are doing, right? So lower means better in this case. So we want to get the value of the weights that minimizes C. So why don't we try and solve for it analytically? Like we all know how to optimize from basic calculus, right? So just take the derivative. What could go wrong? It's only 10K unique weight. Ah, yes, wall of math. Nice to meet you, old friend. Okay, we can't really do an analytical solution. So in that case, let's do a gradient descent. So it's an iterative value. It's an iterative solution, right? So we can't really jump to the value. So let's just walk there instead, right? Let's say that the direction of the steep. Okay, let's talk about climbing down a hill, right? So let's say that we want to get down as fast as possible, right? So what you do is that you basically say, where is it most steep downwards, right? So that you represent that as a vector v. Then you take a step that is represented, and that step has some distance a. So you move some distance alpha in that direction v. Once you finish the step, it might have changed. The direction of steepest descent might have changed. So you check again, what is the steepest, the direction of steepest distance, and then you walk another step alpha in that. And then you go on and on and on down the mountain until you reach the minima, which is our goal. All right. Now, how large should our step be? It's like Goldilocks, not too big, but not too small either. Because if it's too small, you basically keep taking tiny little steps, and it takes forever to complete. If it's just right, you get there in a reasonable amount of time, and your computer thanks you. If it's too high, it can actually explode. You might not even find a minima because you might just jump over the entire minima. So that is one thing that you have to keep in mind. That sort of tuning will be done, that sort of stuff is done in hyperparameter tuning, which Limbe Young will cover. All right. So now as for our weight updates. So let's consolidate every individual weight in the network into a huge column vector theta. Then theta updated is just going to be theta minus alpha v. If alpha is set right, we should be able to reach a minimum, right? We should be able to tweak our weights to minimize the cost function now, correct? Yeah, so I think we've done everything. We basically have gradient descent to find out the minimum of, to basically reach a minimum in the cost function. Once we find a minimum in our cost function, we have trained our network. So yes, good work, guys. Wait. Okay, we forgot to calculate the direction of our descent. Oops, my bad, I'm sorry. So let's look into how we actually calculate that direction. Back propagation. So I mentioned that we needed to try and find the vector of steepest descent, right? But how do you even do that? Well then, if we want to, like in 2D calculus, the concept of the derivative basically is the slope of the function at that given point, correct? Now, let's think about it in a 3D sense. If you look at it in a 3D sense, if you look at it in n dimensions, that idea is encapsulated in the gradient. The gradient returns you a vector of steepest ascent. It basically says on this hill, this is the fastest way to get up. And so how do we get the fastest way to get down? We just have to take the negative of it. If you want, we just have to take the negative of our gradient. So what we need to do now is that we need to compute the negative of the gradient vector. So this is the gradient of our cost function. Each one of these terms is a separate vector. So you don't add them up like scalars. Like this is pointing in the direction of W1. This is pointing for W110. This is pointing in the direction of W111 and so on and so forth. All right. And if we try and compute the gradient from the cost, again, we run into the same issue. The cost function is still way too complex. So this is where backpropagation comes in. All right. So there are three things that you must remember. The weights of the connections determine how much, say, a particular neuron in L-1 has in the activation of a neuron in layer L. If this guy was at 10,000 times bigger than the other two, the output's going to be determined by A1, right? So, and on the other hand, if this was just vanishingly small to zero, it's not going to take this A0 into consideration, correct? All right. Now, the output of a neuron in layer L is determined by the activations of these neurons and the weights of the connections between the neurons. And remember, we cannot actually tweak the activations of the neurons themselves. We can only tweak the weights that we assign to these connections, right? So how do we accomplish this? Well, then let's look at it n backwards. in feed forward, our information goes from the inputs to the outputs, and how exactly it's fed forward is informed by the weights. So our connections to the weight should basically look at our output, and then we should consider what should our input have been to get our output, correct? So that basically means that we need to tweak our weight somewhat, and we need some way to talk about how tweaking to the weights actually affects our overall cost function. And that is represented neatly in the idea of the partial derivative. All right. Now, here is how we calculate the derivative. Now, dou C by dou WLJK. Now, C is basically a cost function, and WL is basically a weight in the last layer. So C is a function of Y, and Y is a function of W. All right. So dou C dou Y is a function dou C dou Y, and dou Y dou W. Right? We can break it that we can break it like that by the chain rule. Now dou Y dou W can be broken up as dou Y hat by dou Z times dou Z divided by dou WJK. And dou Z by dou WJK can be broken up as this entire sum right here with respect to JK. But remember, the weights are independent of each other, so we can ignore everyone over here that is not WLK times AL minus 1 times AL minus 1K, right? So if we do all of that and we just take the derivative like normal, we basically get this activation. We get the activation of that particular neuron itself, right? Now, if we basically, now we can look at a cost function, dou C dou Y. Immediately you can just figure out Y hat minus Y, dou Y by dou Z. That's going to just be the derivative of this. That dou Y hat by dou Z, that's just going to be G of Z of L, which is just going to be G prime of Z, right? Dou C, and then if you put all of these together, if we put every part that we've calculated, like from over here, dou C dou WJK, then dou C dou Y dou Z, all of these together basically gives you this derivative right over here. And this is this gradient right over here. And this is the gradient that we actually need in that is the element in our gradient, all right? Now, if we want to go deeper, keep in mind, if we want to analyze this guy over here, we have to think about what it affects ahead. So this weight affects this neuron over here, and then this neuron basically affects the activation of this output layer, which then influences our cost function, right? So dou C by dou W L minus 1 JK becomes dou C by dou Y hat times dou Y hat by dou Z LK, which is basically the input that comes into here. Then dou Z LK is dependent on this activation right over here. So, and then this activation right over here is dependent on whatever sum came in. And whatever sum came in is dependent on this weight, which is what we wanted to find out in the first place. So so basically information flows backwards. We look at our outputs to see what our input should have been. So we keep doing this for every single node, for every single weight in our neural net in order to get our gradient. We use this gradient to take a single step, improving our net slightly, and we finally stop when our cost function is minimized. So congrats, you now know how a neural net works for the most part. Take a breather, we'll have a break, and we'll go over the math on your own time a bit later. I've had to abridge quite a bit, but then the math behind this is surprisingly elegant and rather beautiful. All right, so we'll pass on to the next speaker.
All right, can everyone see my slides?
Yes.
All right, so this will take about another 10-15 minutes and then we'll go for a short break, all right? Okay, so good evening, everybody. I understand the math that from the previous section was a little hard, okay? But I promise that this section, there won't be any more math. We will cover some of the very important practical concepts before we actually dive into the Google Colab notebook over here. So first up, the method that we talked about earlier is actually known as stochastic gradient descent, where the weights are actually updated through backpropagation after every single observation. Okay, this is actually a bit of a problem because the computational time is extremely high. On the other hand of the spectrum, what we have is known as batch gradient descent. So in batch gradient descent, the weights are actually updated after all observations, which means your entire training data set. This time around, computational time is a little lower, but the computational space required is a lot higher because you have to load your entire training data in memory in order for this method to work. So since both extremes are not too good, what we need to do is to find a balance between the two. And this balance is actually known as mini-batch gradient descent. So in mini-batch gradient descent, your weights are updated after every n observations. So now we're going to give you a term to define these n observations. And this term is known as batch size. Basically, the number of observations that is used in a single iteration. Okay, so this is actually quite an important concept. So what we'll do is we'll do a mini quiz. So in mini-batch gradient descent, where the weights are updated after every 16 observations, what is my batch size? Maybe you can type your answers in the chat and I'll take a look. 16, fantastic. All right, so now let's go to a great. Keep the answers coming in. Let's go to the next question. In batch gradient descent, where the weights are updated after all observations, what is my batch size? Yeah, y'all are wondering, it depends on my training data, right? Number of observations, fantastic. So it really depends on the number of rows of my training data. So let me give you the third question, which is probably the simpler one, the simplest one. In stochastic gradient descent, where the weights are updated after every observation, what is my batch size? Fantastic, Lucas, Gerald, Jiju. All right, all coming in one. Okay, this is the correct answer. Thanks for those who answered. So let's move on to the next part. I'm going to introduce two additional terms. This is known as epoch and iterations. Epoch refers to the number of times that the entire training data, i.e. all the observations, was used, whereas iterations for epoch actually refers to the number of batches of training data in one single epoch. All right, so this is a mouthful. So what we'll do is we'll run through an example together. So we'll look at batch size, epoch, and iterations and see how they are interlinked. So let me give you an example. Let's say I have a data set that has 64 rows of data and 4 columns. And I specify that I want 5 epochs and my batch size is actually 16. So in this example, what is the number of iterations per epoch and what is the total number of iterations that I have? No, okay. So this is a work example. So just to recap, 64 rows of data, batch size 16, 5 epochs. So what is the number of iterations per epoch? So let's just look at one epoch first. One epoch uses the entire training data set, correct? So that would be 64 rows of data. My batch size is 16. So how many groups of 16 can I form from 64? All right, I see the answers coming in already. 4. Lovely. Exactly. So there are 4 groups of 16 that I can form from 64, which means one epoch requires 4 iterations. So now let's go to the second question. It's another very simple math question. So what is my total number of iterations? A single epoch has 4 iterations. 5 epochs requires 20. Fantastic. Thank you for answering as well, Kurusima. Now, another concept that I'm going to introduce would be model hyperparameters. I think some of you are aware of this already, but if you're not, okay, we can just go through it a little quickly. So model hyperparameters is essentially parameters whose value is actually used to control the learning process. It's defined by the user. This is a very important concept. It's defined by the user because it cannot be tuned from the data set itself. This is not the official definition, but keep in mind that these hyperparameters are essentially values that you need to define as a user when you're building your model. And why do we call it hyperparameters and not just model parameters itself? Okay, the reason for this is that we already have something called model parameters. Model parameters are essentially values that can be tuned from the data itself by the model, and it cannot be defined by the user. So to differentiate these two, we call the parameters that we can define as model hyperparameters. So we actually have covered a couple of hyperparameters in the all the way up to this part of this workshop. So some of the hyperparameters that we have covered include the learning rate, the batch size. Okay, iteration is not exactly a hyperparameter that we need to state because it will be auto-determined by the batch size itself. The third hyperparameter that we have covered is actually the number of epochs. And a choice of activation function is also another hyperparameter. So I think a natural question that some of us may have is, what is the best value for each hyperparameter? Because earlier I talked about how we cannot define the hyperparameter, we have to define the hyperparameter values, right? So is there a best value that we can simply use every single time we build a model? The thing is, there is actually no best value. Then if there's no best value, then how do I choose which value I should have for each hyperparameter? So to do that, you need to carry out the trial and error approach to actually find out which hyperparameter is the best for your particular data set itself. How do I know whether the trial that I'm conducting right now with this set of hyperparameters is better than the previous trial with another set of hyperparameters? To answer that question, you need to actually look at two things. One would be your training data error, and the second would be your validation data error. And these two error values will actually give you clues as to whether you're underfitting, overfitting, or whether you're in the right region. If you find that your validation data error and your training data error actually decreases after every epoch, all the way until your very last epoch, it means that you're currently underfitting because there are more patterns in the data that your model can actually figure out, but it hasn't done it yet. So what you need to do is to actually make it a little more complex. We will go through how you can actually make a model more complex in the next couple of slides. On the other hand, if you find that your validation data error, it originally decreased after every epoch and then started increasing, whereas your training data error, it started decreasing all the way until the very last epoch. It means that you're currently overfitting, which means that not only has your model learned all the patterns that exist in the data, it has also learned the noise that exists in the data, which is not what you want. So ideally, we want to be somewhere in this green region where your validation data error is at its lowest, and it's also very close to the training data error. So it's something like this, where your model actually learns all the patterns, but it doesn't learn the noise in your data. So let's look at the underfitting and overfitting steps in a bit more detail. So now, let's say I find that I'm underfitting. What should I do? Yep, we make the model more complex. How can I make the model more complex? Does anyone have any idea? All right, let's go through it. You can add more layers. You can add more neurons per layer. And you can also train the model a little longer. You can increase the number of epochs. So let's say you're on the other end of the spectrum where you're overfitting. What do you do? As some of you may have guessed it, it's essentially the opposite. You make the model less complex. So this involves removing some layers, removing some neurons per layer, and also training the model a little shorter, which means you decrease the number of epochs. Okay, here's the thing about overfitting. Other than doing what I mentioned in the previous slide, which includes removing layers, removing neurons per layer, decreasing number of epochs, there are also some advanced tools that you can use to actually deal and manage overfitting. One of it is called regularization. The second is dropout, and the third is early stopping. Okay, so these are quite advanced concepts, so I won't go into the actual math itself, but I'll just give you a brief intuition and explain to you how it affects the neural network and how it prevents or manages overfitting. So for regularization, essentially what's happening is that you're adding a penalty term to the cost function. So originally your cost is equivalent to the loss function itself, which depends on the metric you have specified, for example, root mean squared error. But with this new penalty term, your cost function is now your loss function plus the penalty term. So the effect of this is that it actually shrinks the weights in your neural network and makes it closer to zero. So this helps with the overfitting, managing overfitting. The next method is known as dropout. So in dropout, at every iteration, you will randomly select some neurons and remove all the incoming and outgoing connections to that neuron. The probability that these neurons will be selected really depends on the rate that you've specified, which is also another hyperparameter. So this one I can give you an example to show you how it works. So let's say I specified that I want a dropout of 25% in the first hidden layer. So the first hidden layer corresponds to the points in green, the neurons in green. So let's say the second neuron was selected because 25% equals to 1 and 4, right? If the second neuron was selected as the neuron to be dropped, automatically all the connections that are incoming and outgoing, which means the 3 lines that you see over here and the 4 lines that you see over here will be dropped from this particular neuron. And the effect of this dropping is actually that it reduces the model's reliance on any single neuron, causing the weights of these neurons to not be overly high. So again, this is another way of dealing with overfitting. You can take a look at the link when we send you the slides for more information as well. And the last step is known as early stopping. So there's something cool about early stopping. So let's say you specified 200 epochs for your model, but the thing is your model starts to reach its lowest point of the validation error at, say, epoch number 20. If you're going to train it all the way to 300, it's definitely going to overfit, right? So there's actually something called callbacks that you can use, so that even if you specified that I want my model to run for 300 epochs, if the model finds that it's starting to overfit after 20 epochs, it will terminate the training at 20 epochs. So this is a function that we will show you how you can code out in the Colab notebook later on. So actually now I've come to the end of the theoretical components, and we'll start moving on to the Colab part where we get to code out and put our knowledge into practice. But before we do that, we'll have a short 5-minute break, all right? Okay, so for this short 5-minute break, and go to the toilet and drink up and do what you need to do. Yep. Hi everyone. I hope the break. I hope the 5-minute break went well. Okay, so can I get you guys to look at the chat? So I've sent this particular link over there, tinyurl.com/intro to deep learning/colab. Okay, I need all of you to actually copy this link and paste it onto your browser. So it should bring you to a page that looks something like this. In fact, it should look exactly like this. So I'll give you about 30 seconds to do that. Okay, so once you have gone to this page, right, can I get all of you to click on File and click on Save a Copy in Drive? Because if you were to make any edits to this particular Colab notebook itself, it won't be saved for you. So in order for you to make sure that your changes are saved, you have to save a copy of it in your own drive. So just give you another like 30 seconds to get that sorted out, and then we will begin the next part. Okay, so maybe you can use the, if any of you need a bit more time, maybe you can use the cross button that you see in your Google, in the Zoom function itself to let me know that you need a bit more time. Okay, I will take a, I'll pause for another like 1 minute. Hopefully you can get it sorted out by then. So the rest of you are okay already, is it? Okay. All right, I'll get started. So I understand that the content earlier again was a bit difficult, right? So in this segment, you'll get a chance to refresh all those concepts and understand the content a little better. And most importantly, you'll get to put all of it into practice. Okay, so this Google Colab portion, right, we actually structured it very, very nicely. So we'll actually go from a very basic model, and then from there, we'll slowly add more and more complexity to that model. And then we will tune the hyperparameters a little, and we'll find that, you know what, this model actually overfits the data. Then we'll add in some elements to deal with this overfitting. So you'll definitely be able to follow this Google Colab notebook, so don't worry about that. And at the end of the day, you will learn how to build your own deep learning model. So let's get started. So first up, I need all of you to run this line of code. So basically to import the relevant libraries that you'll be using for today. Pandas, because we'll be working with data frame. Seaborn, if you haven't seen it before, it's actually a data visualization library, but we are not using it for data visualization purposes. We'll be using it simply for the inbuilt data set that it has. You'll see this later on. The third library that you need to import is matplotlib. This will be for data visualization purposes later on. And the last is TensorFlow, which is the star for today. It's actually the model, it's actually the library you'll be using to create all our deep learning models. All right, so I just want all of you to run these lines of code as well. This is just some extra, slightly complicated looking code. It's just to make our results reproducible. Your results should look something or very similar to what I have, all right? Okay, so first things first, we will actually load Seaborn's inbuilt dataset. This dataset is known as the diamonds dataset. If you run df.hit, you get to see what this dataset actually contains. The dataset actually contains 10 different columns, and 7 of these columns are actually numerical, while the last 3 are categorical. In this high-level overview table, I've actually given you the description, which actually corresponds to what this, and it gives you a bit more information about what each of these columns is about. So for instance, if you look at carat is actually the weight of the diamond that we have. And beneath each of these description, there's also square brackets. In these square brackets, for the numerical columns, I've stated the minimum value as well as the maximum value. So the minimum value for carat that you'll see in this diamonds dataset is 0.2, while the highest is actually 5.01. For categorical, it's slightly different. I've stated the description as well, and underneath the description, I've actually given you all the different values that the categorical column contains. So for instance, in cut, which corresponds to the quality of cut, there are actually 5 different values. It could be fair, good, very good, premium, and ideal. Okay, another thing to note would be the yellow color highlighted row, which corresponds to the price column of our data set. Okay, the reason why I highlighted this is because this is going to be our Y variable for today. We're going to be using all the other columns, caret all the way to table, and X, Y, Z to predict the price. So that's the goal for today. So I want all of you to click on df.shape, 53,940, 10. So this means that there are 53,940 rows and 10 columns of data. And if you click df.info, what you realize is that every single one of these columns that I have, from caret all the way to Z, each of it has 53,940 non-null values, which means that this data set is actually very clean. There's no missing values. Again, df.describe, it helps you visualize this a little better as well. Instead of just seeing the count, you can actually take a look at the minimum, maximum values. This is just to give you a bit more information about what each of these tables is about. We're not going to go through in detail, but if you want to verify that the information here is correct, you can actually go look at the minimum, maximum value. For example, for caret, the maximum is 5.01, the minimum is 0.2. And this is actually what we have written down over here. 0.2 is the minimum value, 5.01 is the maximum value. So what we have written over here is that this data set is actually very clean. We did some analysis as well, and that's why we are not going to actually proceed to do visualization and whatnot, because we want to focus on building deep learning models, which is the main objective for today. So before we go into modeling, we actually need to do some splitting of the data itself. So first up, the first thing we need to do is to separate the X and the Y variables. Y would be price, and the other columns will be assigned to X. And after we are done with this step, what we'll do is we'll go for an 80-20 split. 80-20 split in the sense that we'll keep 80% of the data for training purposes and the last 20% of the data for testing purposes. And to do that splitting for us, we have this train test split function that's present in the sklearn library. So go ahead and click this run for these two lines of code. In train test split, there's one parameter that I want you guys to take note of, which is the train size. So train size equals to 0.8, basically tells you that 80% of the data will be assigned to train X, and the remaining 20% will be assigned to test X. And random state makes sure that whatever the split is, your split and my split will be the exact same split. So we will have the exact same set of rows that are assigned to train, exact same set of rows that are assigned to test. Now that we are done with all this splitting, we are now going to go into the pre-processing stage. So earlier on, we had a couple of categorical columns, correct? 3, in fact. But the thing is, we cannot feed these categorical columns directly as text into the deep learning model because basic deep learning algorithms don't understand text. So we got to convert it to numbers. It's an additional step that we need to take. So just to visualize what are the 3 columns again, it's actually cut, color, and clarity. So if we go ahead and click run on these 3 lines of code, train X, cut, train X clarity, train X color, you'll see all the different categories that are present, which I also wrote down in the table that you saw earlier. So for cut, there are 5 different values. Categories, for clarity, there are 8 different categories. And for color, there are 7 different categories. But the interesting thing about all these categories is that there is a certain natural ordering to them. So if you take a look at cut, ideal is the best, followed by premium, followed by very good, followed by good, and the last would be fair, which is probably the worst. So what we're going to do is that we are going to do label encoding, where we will go to each column, each of these 3 categorical columns, or ordinal columns actually, and then we're going to find every instance of ideal in the cut column, and we're going to convert it to 0. We're going to find every instance of good and convert it to 3, every instance of fair and convert it to 4. And to help us do that, we have this label encoder class in the sklearn library. So go ahead and click run on this line of code. What's going to happen is that, first of all, you're creating an instance of the label encoder class. And then you're going to fit the ideal or your preferred ranking into this particular object itself. Afterwards, you're going to transform the cut column in your train X and the cut column in your test X using the transform method that is present in this class itself. So once you have done that, we will do something similar for clarity, and we will do something similar for color as well. So go ahead and just click run on this line of code and this line of code. So let me just give you a brief explanation. So what's going to happen here is that similar to what we did for cut earlier, you're going to find all the instances of I1 in clarity and convert it to 0. we're going to find all instances of BS1, for instance, and convert it to number 4. In color, we're going to do something similar as well. All the instances of B converted to 0, all instances of J converted to 6. Okay, I just want to visualize this as well right now. So I'm going to click run on these 2 lines of code. So under train x.hit, you notice that previously cut color clarity, they had text, but now there's no more text. It's all in numbers right now. Similarly for, it's all in numbers right now. So, and similarly for test x, all the text is now has disappeared already, and everything is now written in, is numerical. It's all in numbers right now. So what we need to do next is to deal with the numerical columns. We have settled the categorical, we'll put that aside. We'll deal with numerical right now. Okay, so why do we need to normalize the numerical columns? Normalization is actually very important for certain kinds of algorithms, including deep learning algorithms, because it helps to make sure that the gradient descent is able to move smoothly towards the minima, and that the steps that the gradient descent of the gradient descent are updated at the same rate for every single feature. So the overall effect of all this is that it helps the gradient descent to converge more quickly towards the minima. And to do that for us, we have this thing known as the standard scalar object from that we will use from the sklearn library. So for those of you who are familiar with z-score, that's essentially what we're doing. We're going to find the z-score of each individual value in the numerical columns. So click run on this line of code. So what's interesting over here is that we don't actually have to deal with each individual numerical column individually. We can actually deal with all these numerical columns together. All you need to do is make sure that they're all put together in the same list that you create. So we'll do that for train X, we'll do that for test X as well. So it's actually very similar to what you saw earlier. And when you print out test x.hit and train x.hit, what you realize is that now your numbers, your numerical values for caret, depth, table, x, y, z, they're all very different. You have a lot more decimal places in each one of these rows. And this is expected because right now, what we're looking at is not the actual score, it's the z-score or the z value, whichever you're comfortable with. Okay, so this is the second last step that we need to do. There's one final step that we have to touch before we go into the modeling, which is the most exciting part of today. What we're going to do right now is that we're going to split it further into the training and validation. So what I'm doing here is that previously my training data, I had 80% of the original data in train X, but now I want to split it further. I want to make sure that out of this 80%, 60% of it goes to training and 20% of it goes to validation. So 60% of 80% is actually 75% of 100%, correct? Which is why I specified that my train size is actually 0.75. So now what happens is that my original train X, which contains 80% of the entire data set, will now be split into 60% for train X and 20% for val X, which is your validation data. So now we'll create a baseline model with minimum code. But before we go there, I just want you to click on this line of code and see what the shape of the train X is. So what we realize is that there are 32,000 columns, 32,364 rows of data, and 9 columns. And if you look at the model that we're going to build, this is an example of a model that we're going to build right after this. There are actually 1, 2, 3, 4, 5, 6, 7, 8, 9 input neurons. So do you think it's a coincidence that there are 9 columns of data and there are 9 input neurons? Not quite. It's not a coincidence because you need to make sure that the number of input neurons corresponds to the number of columns that you have of your tabular data set. So that's actually very important. Next, in our model that we're going to build, we are going to have a single hidden layer with 2 neurons only. So the number of neurons that we want in this hidden layer is really up to us. But we'll start off small by going with 2. As for the output layer, what we notice is that there's a single neuron here. This is again not by chance because we are doing a regression task and therefore we need to make sure that there's only 1 neuron. If you're doing a classification task instead, then the number of output neurons will actually correspond to the number of categories that you have. You have a data set that has a classification data set that has 5 categories. Then you must make sure that you have 5 output neurons as well. Luckily, we're doing regression, so one will suffice. As for the diagram itself, some of you may notice that the colors are a bit different. The weights of each of these lines is a bit different as well. Okay, this is just an example, so you don't have to worry too much about it. I just wanted it to be a bit more colorful than just drawing black lines all across. So don't worry about the different coloring. Don't worry about the weight or the intensity of each of these colors. It's just for diagrammatic purposes only. So first up, we're going to import two of these classes from TensorFlow. The first one is known as sequential. Sequential is essentially, you can think of it as a container. In this sequential container, you're going to add many layers of the neural network. And it's sequential because you're going to be adding these layers sequentially, one after the other. And the layer they're going to be adding sequentially is known as dense. So dense basically is a densely connected neural network layer that you're going to be adding into this sequential object. So you'll see how in just a moment. So I want all of you to run this line of code as well. Model equals to sequential. So you create an instance of the sequential class. Then model.add dense. So this is where you're adding your first hidden layer. And what you're doing by putting 2 over here is that you're specifying that I want two neurons only in this hidden layer. And take note that for the first hidden layer that you have, you must specify the input shape. So in this case, we have 9 neurons, 9 input neurons. So we have to specify that in this parameter as well. And the last thing to take note of is the activation. So you need to specify an activation function as well. Otherwise, if you have too many, many layers, it's not going to help at all because there's no non-linearity that's introduced to this particular neural network. So 2 things to take note of. One is that you need to add your input shape for your first hidden layer, and you need to add an activation function for all your hidden layers. This is compulsory. You'll see this when we increase the number of layers later on, and how this is relevant and how this works out. So next, what you need to do is click on model.compile. So model.compile, you need to specify 2 things. One is the optimizer. The second is actually the loss function. So in this case, optimizer, I'm using Adam instead of stochastic gradient descent, because in stochastic gradient descent, you need to actually specify the learning rate. For Adam, the learning rate, he will actually determine and adapt it accordingly. So we don't actually have to specify the learning rate. So to make code simpler for you guys, I change it to Adam. We will change it back later on in the later part of this Colab notebook. And for the loss function is the metric that you want to evaluate your model based on. And what your optimizer will do is to try and minimize this particular loss function. So last but not least, you just have to fit your training data, train X and train Y to your particular model. So what you notice over here is that there's very, very little information. With this one line of code, with this one line of output, there's not much that I can actually determine from this, not much information or insights that I can draw from this particular output itself. So what we're going to do now is that we're going to increase the amount of information that we can display in the baseline model. So what we're going to do is we're going to introduce another metric. So earlier on, we only talked about mean squared error. So I'm going to introduce something called mean absolute error. So what I want you guys to do is to click run on this line of code. So this is exactly the same line of code that we saw earlier. But now this time around, in the compile step, instead of just having a loss, we have a matrix parameter as well. And in a list, we stated we want mean absolute error. So this is an additional evaluation metric that I'm going to be seeing in my final output later on. And because this is a list, you can actually go on and state and include other metrics that you actually want to see the output for. So now click on model.fit and fit your training data and training data to this model. And what you notice is that as compared to before, now other than just having the loss, the mean squared error loss, I also have the mean absolute error loss that's given to me. So this part is now new. It wasn't presented earlier on. But this itself is not enough to satisfy me. I want to have a bit more information of the validation data itself and what the performance of the validation data is. So this is what I'm going to do. Now I'm going to run the exact same line of code as I did earlier on. Model.compile is also the exact same line as I ran earlier. But this time around, under the fit step, I also have an additional parameter that's known as validation data equals to, and in a tuple, I'll introduce the X as well as the Y for my validation data. And what you notice is that now, instead of just calculating the loss and the mean absolute error for my training data, I have two additional values that are given to me: the validation data loss and the validation data mean absolute error. So now I have a lot more information to work with, and through many epochs, I'll be able to determine whether my model is underfitting, overfitting, or what. And for those of you who are concerned, are wondering what's the difference between specifying the metrics under loss and specifying the metrics under the metrics parameter. The thing is, your optimizer will focus on minimizing the loss, whereas the metrics is only an additional metric that's calculated just to give you additional information, but the model will not be focusing on minimizing that particular metric. So that's about the difference in case you're wondering what it is. So for those of you who are interested in printing out additional information, you can actually go and click on model.summary. So when you have a model that has many hidden layers, this will be helpful in telling you how many layers you have and what are the different layers like. Now, I have a lot of information, but my model is performing very badly. It's not what I want. I want to try and improve the model a little bit more. So what I'm going to do first is to actually increase the number of neurons that I have in the single hidden layer. So previously what I had was 9 input neurons, 2 neurons in the hidden layer, and a single output layer, a single neuron in the output layer. Right now, I'm going to increase the number of neurons in the hidden layer from 2 to 8. So it's almost the exact same line of code as we had before, but just that now instead of having 2 over here, I've changed it to 8. And when you click on compile and fit, what you notice is that actually the mean absolute error and the validation mean absolute error is actually much better than what we had before. Before it was about 3,900 and about 3,900 as well. But over here, it's actually 387, 378. Okay, it's actually doing quite well. And when I talked about increasing model complexity, another concept I brought about was increasing the number of hidden layers. So previously, we only had a single hidden layer. So let's try experimenting with more hidden layers, from 1 to 3 hidden layers. 1, 2, 3. So this is the line of code that would actually build this particular model. What I want you guys to focus on would be the fact that these 2 lines of code are actually very similar to the first hidden layer, just that it's missing out on the input shape. So as I mentioned before, input shape parameter is only needed to be specified for the first hidden layer. Next, you will click on model.compile. Again, it's the exact same line of code that we had earlier. Model.fit, again, same line of code that we had earlier. Let's see how it performs. Okay, because we only had 2 neurons for each of the hidden layers, there wasn't much improvement to the score. In fact, I think it's slightly worse than before. So let's try something different. How about we combine both the increase in neurons and the increase in hidden layers together? So now it's the exact same line of code as I had previously, but just that now I'll be changing from 2 neurons per hidden layer to 8 neurons per hidden layer. And let's see how it works out. Model.compile, same line of code. Model.fit, same line of code. So previously it was stuck at what, 3,900, 3,700, and now it's all the way down to 2,600, 1,400. Okay, it's actually doing much better than before. So now I'll hand over the time to Wei Lang, who will explain how you can go about tuning the hyperparameters and seeing better results.
Okay, let me share my screen. Can you see my screen?
Yes.
Okay, great. So evening everyone. So now I'm gonna be continuing from where Vinod left off and going through the rest of the notebook where we ultimately create like a deep learning model that's capable of doing pretty well on this data set, right? So I'm going to continue by applying more of the concepts taught in the lecture just now onto TensorFlow. So the first 2 things that I will go through with you is batch size and epochs. So as Vinod covered earlier in the lecture, right? Batch size is the number of samples from training data used to calculate the gradient for a single step, right? So remember that we are doing our gradient descent in mini batches because we can't just take all 50,000 data points, calculate the gradient of the loss function, then take 1 step. That's far too slow, right? So instead we take like, say, I don't know, 40, 50 steps. So the default batch size in TensorFlow is 32. Yeah. So we don't do like one step either, because that's a bit too random. You're not taking into account enough information to make a good step. Yeah. So for epochs is one epoch means that we have iterated over our entire data set once. So if we had like 500 training samples, it means that we have iterated over all 500, and that would make one epoch. So the idea I want you to keep in mind here, right, is that if we keep the number of epochs constant, increasing our batch size would mean that we are taking less steps, right? Because if a single batch is bigger, right, it'll take less batches in order to cover like one epoch or the entire data set. Yeah, so you can see this link for more information. So so far we've been just leaving it to the default, right? So let's try doing a batch size of 128 now. Okay, so I will, this one is already run. So it's the same model as just now with three hidden layers and one output layer. So we compile and then we specify the batch size here at the model.fit stage, right? So we run it and we get a mean absolute error of around 3.9K. So I think that's higher than what we had earlier, right? So earlier we had 2.6K, so now we have 3.9K. Okay, so before I explain what's going on, let's try a smaller batch size of 2. So here we go again. So it's the same thing, except I'm changing the batch size here to 2. So now we can see that the mean absolute error is much lower. It's around 1000. So what's happening here? So the first thing I want to draw your attention to, right, is this number over here. So remember that this number is the number of batches that the model goes through in one epoch. So basically you can take this as like the number of steps it takes in the loss landscape. Right, so you can see that when our batch size is much bigger, the number of steps that we are taking is a lot smaller. So it's around 250 versus 16,000 steps in the case where our batch size is small, right? So this means that as we are taking more steps when the batch size is small, we are ultimately converging onto like a better set of weights, even though like each step may be less accurate, so to speak, because we are using less data to calculate it. Yeah, so this is our key observation from here. So a smaller batch size leads us to a more optimal value within a single epoch because we are taking more steps within the epoch. Okay, but there's a caveat. So if you run this on your own end, right, you observe that the case where our batch size is small takes a lot more computational time compared to the case where our batch size is big. So this is likely because there's more overhead from just simply taking a lot more steps. So 16,000 steps versus 250 steps. So this is, you constantly have to update your model in this case. Yeah, it's less parallelizable. Yeah. So the next thing we're going to try is to increase the number of epochs to 10. So so far we've just been doing one epoch, right? Just a single iteration over the entire data set. So now let's try doing 10. Okay. So I already ran this code earlier. So you can see that now you get a lot more information out, right? See, each epoch is labeled, and in each one you have 1012 batches exactly. So what can we observe? We can see that the loss is gradually going down as we continue to train our model over the data set again and again. And this applies to the validation loss as well. Okay. So yeah, so I think this is pretty intuitive, right? The more you train your model, the lower your loss will become, right? Well, not exactly, okay? This may not always apply to the validation loss, but for our test training set loss, then yes, it definitely would keep going down as you train your model, because ultimately you are trying to fit your model to your training data. So it makes sense that the loss will constantly decrease, okay? But for validation loss, it may not be the case because you are not fitting your model to the validation set. You are fitting it to the training set. So if, like, for example, if you maybe like train 1,000,000 times, then you just memorize all the training data, right? It will result in the thing we described earlier called overfitting, where you are overfitting to your train data and it doesn't generalize well to your validation data. So in that case, you see your validation loss start to go up after a while. Okay. So anyway, in practice, right, what we want to do is we just keep training our model over and over the data set until we observe that our validation loss has started to increase. But we didn't do it here because we want to save some time. Okay, so far so good. Next, so we're going to try tuning more of the hyperparameters in our model. And the next thing we will try is to change the optimizer we used. So I think Vinod talked earlier about this thing called Adam that we are using, right? So this is a more complex optimizer as compared to like the basic stochastic gradient descent that we learned about in the lecture, right? So it's the default one used by TensorFlow actually, because it's been empirically shown to provide pretty good results over like regular stochastic gradient descent. Okay, so how does it work? It's pretty complicated and mathematically involved, but what I can share with you here, right, is that first of all, it includes this idea of having momentum. So what does momentum mean? So if you picture it as a 3D loss landscape, right? You're trying to navigate to the lowest point in your loss landscape. So like it's kind of like a ball rolling down the hill, right? So momentum is basically when the ball, right, doesn't want to change direction so quickly. You know, like in this case, right, you can see that without momentum, it's just zigzagging, right? Because you calculate the gradient of your batch at that point. So whatever it is, you just go in that direction. But with momentum, right, you take into account the directions, the change in weights from past iterations, and you take that into account in your current step take. Okay, so in that sense, it's a bit like the momentum you see in physics, where the ball doesn't want to change direction so quickly when rolling down the hill. Yeah. Okay, so that's momentum. And then there's also something called adaptive learning rate. So basically the learning rates will change depending on the situation. Yeah. So our choice of what optimizer we use, right, will affect how quickly we converge on a local minima in the loss landscape, and also whether we even have conversions at all, right? So if you want to learn more about optimizers, you can check out these links over here. Okay. So let's try using just basic stochastic gradient descent and seeing how it does. So again, I've already run this. So what we do is we create our optimizer object. So tf.keras.optimizers.sgd. Then we set the hyperparameters. So in this case, I chose something very small for the learning rate. Okay. And then momentum, I disabled it and all that. So it's just basic stochastic gradient descent. All right. So after that, then we just run our model as per normal. And you can see that the conversion seems to be a lot slower now. You see, we start at around 3.1K, right? And it's only going down very, very slowly. Okay. So that's the effect of having a different optimizer. So let's say we think, okay, this is too slow, right? So let's say we increase our learning rate to something ridiculous, like 1. Okay. Then you can see what happens. Right. So you see all this NAN here, right? This means, right, that your weights have probably just exploded because now your loss, right, is like infinite. Okay. So that's what happens when you set your learning rate too high, right? You are, instead of rolling down the slope slowly, right, your model is just like shooting all over the place, and like you don't really know where it ends up really. So yeah, so that's why using like default SGD, right, is a bit more tricky to use because you have to customize your learning rate. Like it's not like Adam where it's adaptive, right? It really does a lot of things for you. Yeah. So that's the optimizer. Okay. And then the last one other major thing that was talked about earlier, right, is activation functions. So remember that we are using rectified linear units, ReLU. So of course, there are other activation functions you can try at each layer as well. So for example, sigmoid, hyperbolic tangent. So yeah, you can check out the documentation for the list of built-in activation functions that TensorFlow has. So I'll just show you quickly. So you see, it has a whole bunch of different activation functions that you can try out. And it's pretty easy to use. It's just plug and play, right? You just have to change the thing here. Yeah. Okay. So I won't do it for you. I think you can just try this out by yourself. But generally, ReLU is popular because it usually works well in most situations. All right. So anyone got questions at this point? No? Okay, all good. All right. Okay, so the next section, right, will be on dealing with overfitting. So overfitting is the thing where that was talked about earlier. Okay, so so we can define overfitting as like when our training loss is very low, right, but somehow our validation loss is very high. So in that case, we can see that our model has overfit to our training data, but it's not generalizing well to our validation data. Okay. So first of all, right, you're gonna use this extension called TensorBoard. So it's a pretty useful thing that lets you monitor and visualize your machine learning, or rather your deep learning experiments. Yeah. So this is just some code to load it in. So this line here clears the existing logs on the computer. This one loads the extension. This one sets the directory where you save your log while training your model. So in this case, I just put log/fit and then the current time and date. Okay, and then this is to create like this thing called callback object that basically lets you plug into the model while it's fitting the data. Then it lets you see, it lets it access the data even while it's still training. So you can imagine like you see the data being plotted on the graph like as the model is being trained. So you see more and more epochs as time passes. Yeah. So so and then this one is to just load the TensorBoard and then to tell it where you stored the logs of the training. Okay. So this one I've already trained all the data. So you can see here that it's all like numbered by time and date. So there's probably a better way to actually name this, like maybe give it a proper name or something. But yeah, this works in the page. So yeah, it's pretty useful. It's interactive and all that. I can show like different graphs. You can scroll in, you can scroll out. And then there are a lot of other useful little functions. So like you can see, so this one doesn't work because I didn't actually run this on this Colab computer. But you can see like something like visualization of your model's weights, the graph of the internal model itself, that kind of thing. Okay, so you can explore this thing on your own, but it's pretty useful for visualization while training your model. Okay, so right, back to overfitting. So what's the first thing we can do? So the first thing is called early stopping. So remember I was talking about how like your training loss usually keeps decreasing while you train your model, but your validation loss will increase beyond a certain number of epochs. So in that case, a pretty obvious strategy, right, would be to just stop training when you detect that your validation loss has started to go up, right? So that's why it's called early stopping, because you stop training your model early. Okay. So first of all, right, I'm just gonna create a more complex model that is capable of overfitting to the data set. Okay, so now instead of 8 neurons, right, which was like a toy model, now it has 256 neurons and like 4 hidden layers. Okay, so this is a much more complex model, and because it's so complex, it's more capable of basically memorizing or just like overfitting to the training data. Okay. So then this part is the same, the compile step. So again, you see this thing called the callback object. So that's that's a part of TensorFlow, and it's used when you want to plug something into the model while it's doing like compile or fit. So in this case, early stopping stops the model during the fit step, right? So you have to create this callback object to as a parameter into the fit function. Okay, so here we just change out the parameters. So the metric is what metric we use to judge like when to stop training our model early. So we use validation loss. Minimum change is like what counts as an improvement such that it restarts the counter before it stops the training the model. So we put like something like 50,000, which is pretty small in the context of the overall loss we've seen so far, right? So yeah, loss is like something huge, like 1 million. So 50K is like nothing much. Okay, let's go back here. All right, and then patience, right, is just the maximum number of epochs of no improvement that we will tolerate. So in this case, I put 50. I'll explain my reasons later. Okay. Anyway, so here we go. We create our callback object for early stopping. We just provide all our metrics here. And then we just provide it to the fit function here. Callbacks, then you provide a list of all the callback objects that plug into the model. Okay. And then this history thing, right, is an object generated by the model during fitting, and it can be used to, it basically provides all this data here in like a nice dictionary. So that lets you plot graphs manually if you want. Okay, so I really run this because it takes forever to run, right? It's like so many epochs. So you can see that the validation loss at the start is pretty high, and then it goes down, then it goes back up, then it goes down, 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 down. So maybe I'll just show the graph. Okay, so this after plotting the graph. This here is just some code to plot the graph. Remember the history object I was telling you about? So this one basically uses the history object to get the data and plot the graph using matplotlib. Yeah. All right. So this is our training and validation loss graph. So yeah, you can see that training loss, as I was saying, it always goes down, right? But validation loss is different. Okay? In this case, it went down, it went back up, then it went down all the way again. And then at this point, the model decided to do the early stopping thing because there hasn't been any improvement, which was defined as like going down by 50K, right? In 50 epochs. So now you see the reason why I put the patience as 50. Anyone, do y'all get why? Anyone want to make a guess? So someone said stop after 50, not exactly. So remember, patience is the thing that says like after this many epochs of no improvement, right? Stop training the model. So let's say, imagine if I had set it to something low, like let's say I set it to after 2 epochs of no improvement, stop training. Then what will happen here? What do you think? If you look at this graph, anyone got idea? Nope. Okay, so it's pretty straightforward. So basically, right, if I set my patience for early stopping to 2, right, basically you see this part where the loss is going up, right, over like maybe around 10 epochs, right? So basically, it will have stopped training like somewhere around here because the patience is for no improvements only 2, what? So you see this part, it stops improving for quite a long time, like from here all the way to here before it starts going back down. The minimum starts dropping even more, right? So yeah, so if my patience was too low, right, I wouldn't have like gone past this valley over here. I would have just stopped training here, thinking that this is the best result I'm going to get from this neural network, which is not the case. So yeah, so you gotta be a bit careful when doing early stopping. So sometimes it may be worthwhile to just, train the graph over a lot of epochs and plot the graph. I mean, train the model over a lot of epochs, plot the graph and see what happens. Yeah. So yeah, so that's a lesson. Just be a bit careful and relying on all these inbuilt functions. Okay. So yeah, so if we look at this, we can see that ideally maybe we can stop around 80 because there's not much improvement already. Okay. And then the early stopping thing, right, can actually help us automate this because just now there was a restore best weights parameter. So basically it means like at the very end, right, it will restore the best set of weights to the model. So best being defined as the set of weights that gave the lowest validation loss. Yeah. Okay, so that's early stopping. Dropout, I think, was covered earlier as well, right? Where we just randomly disable a bunch of neurons in the layer during training. So this forces the network not to overly rely on any one node, and it prevents it from memorizing the data set. Okay, so how do we do dropout? We just, again, it's all pretty simple, right? It's all just inbuilt into TensorFlow and Keras. So you can just import the dropout object. And then after that, right, you just add it to your model. So like after every dense layer, you just add a dropout layer. So this 0.2 is the percent of neurons I want to drop in at any instance. So this means 20% of my neurons will be disabled at random at any time. Yeah. So yeah, so I just add the dropout layers after every dense layer. And you don't add it after your final layer because this is the one that generates the prediction, right? If you drop this neuron, then what prediction are you gonna have? Yeah. Okay. So then after that, it's all the same. Oh, so one thing to note, right, is this tensor board thing, right? You need to redo the callback object again because if otherwise, right, this log directory is gonna be the same as what it was earlier, right? And it's gonna override the previous model that you trained. So if you don't want that, right, you need to set the log directory to something else. So in this case, it's my current time, right, which will be different from earlier, and then just create the object again. So I just train my model, same old, and then over 200 epochs, and then I plot my graph. So here we are. So you can see, right, that ultimately, right, the validation loss that we managed to achieve at the end is quite a bit lower than what it was earlier without our dropout layers. So you see at the overfitting stage, right, the best we got was around 1.2, but over here, you can see that we managed to get all the way until 0.5. And our validation loss is a lot closer to our training loss. Just now, it wasn't the case. The training loss was very low, but the validation loss was very high, which is a very key indicator of overfitting. So yeah, you see this, like the training loss is so low, but the validation loss is pretty high. So this is a very obvious sign that your model is overfitting, and you should use more ways to prevent overfitting. Okay, so that's that. Yeah, and then the last thing I'll talk about is called regularization. So basically, we add an extra term to our loss function that will penalize any large weights or biases created in the model. So basically, it tries to prevent the weights or biases from getting too large. Yeah. So we can set the amount of regularization we want as a hyperparameter in our model. So it's yet another hyperparameter, basically. So we're going to use something called L2 regularization. So basically, it tries to control the square of the weights. Yeah. So just again, import the thing, create the object, set what level of regularization you want, make the tensor board callback again because you're training a new model. And then here, right, you can see that all you need to do is in each layer, right, you add in this regularizer. So kernel regularizer is for all the non-biased weights, and bias regularizer is for the biased weights. So we want to regularize both, so we just put it for both. Yeah. And then after that, you just compile and fit as per usual. So down to the graph. Yeah, so in this case, it doesn't seem to have done as well as my as the dropout layers. So it's possible that there wasn't enough regularization. So that's why there's still quite a bit of overfitting, as you can see from how training and validation loss are pretty far apart. But if you compare this to the earlier one, right, like you see, it got all the way to around 1 or 0.95-ish, right? So that's still better than the model without regularization. Yeah, so I guess it's a hyperparameter you have to tune along the way, and it may have been a bit weak in this case, but it still seems to work, as we can see from the graph. Yeah. Okay, so I'm almost at the end, right? Great. So the final model. Yeah, so first of all, right, for our final model, we want to use as much data to train it as possible. So we are going to combine our training and validation data into one data set, okay? And then after that, we'll use it to predict our test data. Okay, and then as a basis of comparison, right, we're going to use a traditional ML model called random forest. So this is a pretty powerful model for structured data in particular, and it performs very well out of the box. Okay, so this is just some code for importing it from scikit-learn, and then it's pretty straightforward, right? You create an instance of the object, you fit on the data, then you generate predictions, and then you get the mean squared error of your predictions versus your truth values. So in this case, our mean squared error is 312K. So that's our basis of comparison to the neural network. Okay, and then our final neural network, right? We will use the one with dropout since that seems to be the one that did the best out of all the overfitting techniques. So it's the same old here. So you just create your model, you compile it, then you fit on our expanded training data set. Okay, so train. And then, so what happens at the end? So first of all, right, just as a sanity check, I just printed out the first 5 predictions by each of the models and then the actual prices. Okay, so we can see that actually it's not so bad, right? Like the actual price is $700, I think, and then the neural network said, oh, it's 900. The random forest got quite a bit closer, lah. Yeah, and then maybe we take another one like this one, 11.6 thousand is the actual price of the diamond. Random forest said 11.3, neural network said 11.58. So in this case, the neural network is actually closer. So yeah, it depends on the data actually. Yeah, in some cases the random forest did better. In some cases the neural network did a bit better. But you can see that it's pretty close to the actual prices. It's not giving you something like totally far off or something totally ridiculous. Yeah. So then we just evaluate it on the entire test data set, and we can see that our mean square error is 378,000. So it's pretty close to the random forest one, and I think this is a pretty good result actually. Yeah. So I mean, especially if you compare it to what we had earlier, right, at the very start, like maybe let's say this model, right? You can see that the mean square error was what? 3 million? Oh no, 30 million, right? So 30 million, that's terrible. But now we've gotten it down to 300,000. So yeah, that's not too bad after all our tuning and trying out different techniques. So of course you can improve this even more by trying some hyperparameter tuning. Like you try out a lot of different combinations of hyperparameters and then seeing which one does best. Yep. So but we didn't do this because it takes a lot of time. Because just to train this one model takes like I don't know, 20 minutes or so. Yeah. You can try on your own later. Okay, so I'll just conclude now. So in the workshop, we use a neural network for this structured data set to show that they are widely applicable to most problems, most machine learning problems that you may encounter. But of course, like we advise you not to forget about all your other traditional machine learning models as well, like your support vector machines, random forest, decision trees, that kind of thing. Okay, so while neural networks may be very powerful, it's not like the magic solution to every single problem. Okay, but they do have their strengths, which is why they are so popular nowadays. So first of all, right, it's super good for unstructured data, like audio data, image data, compared to your traditional methods, because the hierarchical structure of your neural network, right, in each layer is connected, each layer, it allows it to learn its own features from the raw input data. So like, for example, you have an image, you can learn the edges, then you can learn the lines, you can learn the shapes, and so on until you get more and more complex things, which allow you to finally like make a prediction like, is this a cat or is this a dog, right? So if you were using a traditional technique like I don't know, a random forest, right, it doesn't work so well on this kind of unstructured data because it's all like pixels one by one, and then each pixel itself doesn't really tell you much. You have to take advantage of the structure of the image itself. Yep. So yeah, and if you were to use traditional methods, you actually have to process this data and get like useful features out of it before your normal methods will work. Okay. So, and the second thing is neural networks scale very well with big data, like huge amounts of data. Like the more data, the better for neural networks. But this may not be the case for your traditional techniques. Okay. And then so these are its strengths, but there are some weaknesses as well. So the thing about huge amounts of data, right, is that it requires a lot of data to achieve good performance in general. So if you have not a lot of data, it may be better to use a less complex traditional machine learning model. Like, I don't know, even a linear regression line may be better. If let's say you only had 10 data points, right, your neural network is not going to do well. Yeah. So, and second point is that it's computationally very expensive to train. Like, it takes a lot of time, it takes a lot of processing power. So For example, our final model took like 20 minutes, but the random forest, right, only took like a few seconds, like maybe 20 seconds or something like that. So you can see that the neural network is much more expensive to train, given how many neurons, how many weights it has. And even in some cases, especially for more complex networks, you need to use a GPU or a graphics card because your CPU cannot do the calculations fast enough. It's going to be very slow. Yeah. So fun tip, right? On Colab, right, you can change your runtime type to use the GPU or even this tensor processing unit if you need to, right? But in my experience, GPU is pretty fast. This one takes, the TPU takes a lot of effort to get it working correctly. Yeah. And in this particular notebook, right, you don't need the GPU. The CPU actually seems to be fast enough, probably because our models are not that big. So it doesn't really take advantage of the power of the GPU in doing a lot of computations at once. Yeah. Okay, so finally, neural networks may not be as interpretable and easy to understand why it did certain things compared to traditional methods. Because you see, like, it's so complicated, right? So many weights and all. But maybe something like, I don't know, a simple decision tree is easier to tell why it made certain predictions. Yeah. So as with all models, neural networks have their strengths and weaknesses, but it's a very powerful technique today, and it's definitely something that you would find useful if you continue to do like machine learning projects. Yeah. So I think that's it from me. We'll hand over the time back to Rayan. Rayan, are you there? Hello? Yeah. Yeah. Okay, in the meantime, if you all got questions, feel free to ask, like in the Zoom chat or on the Slido.
Okay, are you able to see the screen?
Yes.
Okay, so just to summarize what we have learned today, we learned how cool deep learning is during the introduction, and we learned the components of a neural network. And then we learned about feed-forward backpropagation, basically knowing how a neural network works. And then we learn how to evaluate the output to see whether is it a good one or a bad one, and whether should we run again. And lastly, we learned how to train the model through the demonstration. So here's a message to all the participants. Do check your inbox for a post-workshop email. We will be sending the link for the slides, the code, and also the recording for this session. Yeah. So please give us your valued feedback at intro to DL-feedback. All your feedback is appreciated, and I'm pretty sure that all our presenters would really love to know what you think of the sharing. Yeah. So yeah, intro to DL-feedback. Make sure you click on it and yeah, give us a feedback. Okay. And so lastly, do stay updated with the latest workshops and events. So if you have not joined our Telegram group, do join, because we do post our event and workshop shoutouts there. And you could join our Instagram and our website, or you can just view the link tree for all the shortcuts to all the links. So with that, we will end our presentation. So thanks for coming today, and wish you guys all the best.
And thanks for coming. Bye bye.
Thank you.
Thanks,
Bye.
all. I know it was like very, very intense at times, and I apologize.
We stop the recording now. Yeah.